Hello and welcome to this workshop on mathematics and programming. This workshop is about two things. Number one, an introduction to discrete mathematics. Number two, how discrete mathematics will help you become a better programmer. And of course, if you are a software developer or someone in data engineering or someone who wants to get into either one of these fields, then this is something you want to pay attention to and even make an investment in learning. Now, in order for us to understand discrete mathematics, we have to also touch on other mathematical branches, which is what we will do, and which is why this session is titled Mathematics and Programming and not just Discrete Mathematics and Programming. So let's look at the agenda. Here's what we will cover. First, an overview of computer science. We want to make clear what this discipline is about, and so you can better appreciate the role of discrete mathematics in computer science. Now, discrete mathematics, and I want to uh, take you back to comments I've made before about discrete mathematics. It is one of the branches of mathematics that requires no prerequisites. And what do I mean by prerequisites? Say, with calculus, if you want to be able to understand differentiation and integration, the prerequisite for single variable calculus is algebra. So you cannot just jump to calculus without having some exposure to at least elementary algebra. Or, for example, if you want to study probability theory, if you're data scientist, this is something at the center of mm, what you'll have to learn. Probability theory has a lot of prerequisites, something that is not even pointed out in many of the textbooks. Probability theory has prerequisites in single variable calculus, linear algebra, abstract algebra, and discrete mathematics. Now, discrete mathematics by itself has no prerequisites. So, what I mean is this: if you're someone who has taken high school mathematics and you don't even remember uh, classical algebra, things like finding the square root, uh, you know, algebraic properties like associativity, commutativity, that kind of stuff, right? The quadratic equation functions. If you don't even remember those, and even if you haven't taken those, you can still start with discrete mathematics. Why am I even making this point? Because discrete mathematics covers the most fundamental mathematical concepts. Concepts that you will encounter in all of mathematics. You see, one of the problems with learning, one of the obstacles to learning mathematics is the symbols. This is something I always say. There are two obstacles that you will encounter when you uh, want to learn anything in mathematics. One of them is the symbols, the meaning of those symbols, and the terminology. Studying discrete mathematics will expose you to both the symbols to which I'm referring and the terminology. So if you want to become very proficient in any mathematical branch, whether you want to be a computer scientist or a data scientist, discrete mathematics is the place to start. And should you learn discrete mathematics, you can then continue developing your mathematical knowledge and enter the realm of pure and applied mathematics. I will talk about we will talk about pure mathematics as well. Then we will jump into the different subjects that are within the topic of discrete mathematics, including logic and propositional calculus and how they relate to computer algorithms, computer programming algorithms, data structures, of which there are two categories, linear and nonlinear. If you have heard of binary trees uh, and search algorithms on binary trees, and if you want to know how those work, and even how more advanced data structures and algorithms work, then graph theory is something you definitely want to look into. You cannot be a computer scientist if you don't know graph theory. And then we will do two things after that introduction to these concepts. We will look at the applications, the direct applications of these topics in discrete mathematics, followed by a tutorial where I will take you to VS Code, which is just some code editor, and I will show you uh, some mathematical syntax and in parallel the Python version of it. So I will show you a programming implementation, which most of you are probably familiar with. Even if you don't know Python, you'll be able to make sense of the code. So I will show you the code version and the mathematical version of the same concept. And then, of course, a few comments about an up-and-coming course called Mathematics and Programming, which is a 3-week course that will cover computer science, discrete mathematics, and advanced programming. So let's jump into computer science first. These are 6 of the 40 courses you would find in a computer science degree, a 4-year computer science degree, assuming it is accredited by the ABET. Then, out of those 40 courses that you'll have to take to graduate with a 4-year degree, these 6 are the most important. And you can see here that computer programming is only a small part of computer science. Computer science is a mathematical discipline. More specifically, it is applied mathematics. Let's go through these items quickly. So we have computer programming, of course, where you learn things like functions, variables, control statements like for loops, if and else statements, right? Classes, objects, that kind of thing. Then we have perhaps what is the most important of them all, for at least if you're a software engineer or a data engineer, you will have to be a master of data structures and algorithms. So this is perhaps the most important course of them all. And in order for you to be a master of this very important topic, you need to be able to read and understand the contents in discrete mathematics. So if you were to pick up a discrete mathematics textbook, and really, you can cover discrete mathematics in one textbook, which is not true for a subject like probability theory or calculus. For sure, not calculus. It will take a couple of books to cover, at least linear algebra even. So you will need multiple books to refer to if you want to be good at those books. Whereas discrete mathematics, really, there are few books that are self-contained, and those alone you can learn alone from those books. Well, my point is this, really: if you want to be an elite software engineer, an elite data engineer, if you want to be someone who is able to work with and produce very, advanced algorithms for solving very complex problems, then you have to be a master of data structures. And in order to be a master of data structures, you have to be very proficient in discrete mathematics. But moving on, the first 3 are very mathematical in nature. The next 3 are very, hardware related or applied mathematics. So we have computer networks, which is systems that facilitate communication between computers. The internet is a very big part of a course on computer networks. Operating systems. An operating system is the biggest unit of software on any computer. And then computer architecture, which is how you are able to interface with the hardware through software. So if we have the computer hardware, then we have an abstraction called computer architecture, and then we have low-level programming language, and then on top of that, you have a high-level programming language like Python, Java, PHP, JavaScript, etc. So if you want to be a master of computer science, these are the 6 topics you need to, know very well. But if you want to go to the next level and be able to work on all kinds of algorithms, then your priority would be data structures and algorithms. And in order to get to that point, you must be very comfortable with discrete mathematics, which is what we're about to talk about today. Now, before I talk about discrete mathematics, I want us to first talk about pure mathematics, because I want to start with 2 important definitions, 2 important terms, to which we will be making reference throughout this workshop. And in fact, you'll be finding references to these words throughout mathematical literature. Okay, so if you remember what I said there are 2 obstacles when you learn mathematics. Number 1 is the symbols. Number 2 is the terminology. We're addressing the terminology right here and right now. A mathematical object, and this is a very high level definition, okay? A mathematical object is something that you can put inside a collection and to which certain operations apply. Now, this is a very, let's say, vague definition, but I'll give you an example of what a mathematical object is. An integer or integers. Integers are objects that you can put inside a collection. The integer number system is a collection of integers. And these are objects to which you can apply operations like addition, subtraction, multiplication, right? These are things you can do to integers. So that's one example for mathematical objects. Real numbers are also mathematical objects, so are complex numbers. Sets are mathematical objects. Matrices, vectors, tensors, we have these things called spaces, and fields and groups and rings. These are words from abstract algebra. You may have heard of these. If not, you definitely want to put time aside to also be clear with these with concepts in abstract algebra, which I'll also come to. So that's a mathematical object. I gave you some examples. By the way, if you're watching this, check out the video description, where there will be a link to a document where these words that I'm using, these terminologies to which I'm referring, will be defined in that document, and they will be accompanied with examples. So if I say the word space, and then you want to know what that means, you can check the video description, go to that link. You will find the definition for that word and an example to make especially clear what that word means. So that's a mathematical object. Now then we have something called a mathematical structure. A mathematical structure is something that contains a mathematical object. Again, a set can also be a mathematical structure. If you have experience with programming, like Python, we have these things called lists and sets and tuples, right? You can put elements in them. Well, you know that in Python, a list can not only contain things, but a list itself can be put into another list. So, and the same is true for a set. So a set itself is a mathematical object, but it can also be put inside another mathematical object. So you can have a set inside a set. Now, the outermost set we call the structure, and its elements we call a mathematical object. So it's relative. Okay? And once again, we will look at an example of this to make it very clear what uh, we mean by these words. So here's an example. This is a set. In math, we indicate sets with curly brackets, and it has in it some objects. What are these objects? Well, they're integers 1, 2, 3, 4, 5. So these are mathematical objects, and the set that contains it we call a mathematical structure. Pretty easy. Okay? So keep those words in mind, because we will be making references to those words as we go along in these subsequent slides. What is pure mathematics? And I'm sure, or I assume you have heard of something called applied mathematics, and you may wonder what these two are and how they are different from each other. Now, the definition I am going to give you is based on what I have read in a very well-known book called The Princeton Companion of Mathematics. The Princeton Companion to Mathematics. In that book, they say that there is not a clear distinction, and it is debatable as to what constitutes pure mathematics and what constitutes applied mathematics, and this is why I have here two overlapping diagrams. But to keep it concise, I will give you this definition. First, mathematics. What is mathematics in its entirety? One common definition is that mathematics is a language. Just like English and German and Mandarin are languages, mathematics too is a language. The difference is mathematics is the language for expressing ideas very precisely, which is not true for other spoken languages. So just like in English, we have vocabulary and grammar rules, we have vocabulary and rules in mathematics. But it's a language, all right? Mathematics is a language, and of course, if you want, you can also say it's a collection of ideas. Collection of very brilliant ideas, of course. All of them communicated in a language of precision. What does that mean for applied and pure mathematics? What does it have to do with this discussion? Well, applied mathematics is about how you use that language. It's about how you use this language to solve problems in the real world, in the real physical world, whether it is at the atomic level or in the cosmic level. Whereas pure mathematics is about the language itself. It's the study of the language. So you're not using pure mathematics to, send a rocket to Mars, or at least that's not the direct intention. Rather, it is to define things. For example, in English, we might have a debate. What is a noun? What makes a pronoun? What are the rules that a word must follow in order for it to be considered an adjective, for example? So that's really it. Applied mathematics is how you apply mathematics to solve a problem, like in physics or any of the engineering disciplines or computer science, whereas pure mathematics is about mathematics and its rules. Now, again, what does this have to do with discrete mathematics or programming? Again, I want to bring you back to what I said at the start of this session. There are two obstacles to becoming proficient in mathematics. And you don't need me to convince you of this statement, that if you are proficient in mathematics, then you can be proficient in anything, in any of the mathematical disciplines, whether it's physics, economics, data science, you name it. If you know math, then you can do whatever you want. But most of the time, uh, people have a sense of urgency about solving a particular problem and learning enough about this language we call mathematics to the extent that allows them to solve the problem. And they may not, be too concerned about all of the symbols and terms and rules, you know, pedagogical and philosophical uh, concerns. It'll just learn enough to solve a particular problem, and this is especially true for computer programs. Learn enough, or learn the bare minimum, just to be able to build an application or implement a certain algorithm. The problem is when you have this approach, you will plateau very quickly. You will make a lot of progress at the very beginning, but then very soon uh, you will plateau. You will get stuck. You will not be able to go very far. And there is a wealth of information that is produced every day in the form of academic papers about solving all kinds of complex problems. Let me say that again. There is, in academia, a lot of great academic papers written about computer science and machine learning. But to the broader community, this information is not accessible. And I don't mean it's not hard, it's not easy to get a hold of such a paper. I mean in the sense that it's not easy for them to read it and understand it. Because these papers are, well, expressed a lot in mathematics. There's a lot of mathematical explanation. And if you cannot read them, well, you won't be able to interpret. You will not be able to interpret them. And if you're not able to interpret them, then you won't be able to implement them. So how do you stay ahead? How do you put yourself in a situation where you can read any type of paper and stay ahead? Well, you want to pay more attention to the symbols, to the rules. So you want to have the mentality of someone in pure mathematics. If you learn the language early, it will pay dividends in the future. You will be able to progress a lot faster than if you try to stumble along the way and learn whatever you can along the way. All right? This is what the session is about, and this is what the course is about. It is about teaching you the language properly and teaching you to independently learn the language going forward. All right. That's enough with this section. Let's move on. Now, pure mathematics. If you pick up a book on pure mathematics and you look at the table of contents, you will find different subtopics. But this is the one that I think is appropriate. And this is based on some books on pure mathematics that I've come across. So, sets are at the very top. Sets are ubiquitous to all of mathematics. They're not difficult to learn. The syntax involved is very minimal, but they're quite powerful topics. And many ideas have derived from sets. And we will cover sets, of course, in the tutorial. Then we have logic, the study of logic, and something we call propositional calculus, the calculus of truth statements. Again, this is relevant to writing algorithms because in algorithms we have control statements. And some control statements can become quite elaborate. Furthermore, a very important skill for any mathematician is being able to write and understand proofs. While understanding propositional logic is central to being able to read and perform proofs. Once again, we will look at propositional calculus in the tutorial. And then we have something called an algebra. Now, when I say algebra, I'm specifically referring to an algebraic structure. If you remember in the previous slides, we talked about something called a mathematical structure. Well, an algebraic structure is a type of mathematical structure. Things like fields, rings, and groups. These words that I just brought up, you will find in you can find in any mathematical literature. And you need to be able to understand what the author means when they say, for example, this is a field or these following elements. If you're a data scientist, for example, and you want to understand how some very advanced machine learning algorithm works and how it is implemented, you will find the formal definition of that particular model in a book or in an academic paper, and they will invariably, or very likely, I should say, refer to mathematical structures that are discussed in abstract algebra. Moving on, we have then something called congruence, which is really about divisibility and integers. And how is this relevant? Well, in cryptography. Cryptography at its core has or uses prime numbers. And what is the definition of a prime number? It is a number that is either divisible by itself or 1. Now, that is a very small insight into how cryptography works, but again, this is something, if you want to understand cryptography, you have to read Discrete Mathematics. And by the way, if I can just make a comment here, Discrete Mathematics is a subset of pure mathematics. And I will show you the subset in a second. But let's move on very quickly. And then we have relations and functions. A relation is a description about how two sets are well associated with each other. And functions, well, there are two ways to look at functions. There is a map perspective. There's something we call a map, which basically is something. A map is something that takes elements from one domain and maps them to an element in another domain, in another set, I meant to say. So we have the domain and the range. Another perspective of function is something to which you assign arguments, and then you have some internal operation, and from which you will have an output. And yet another perspective is that a function itself is another relation. So maybe these are not helpful terms unless, of course, we start writing some mathematics, which, of course, we will do. Counting, or more broadly speaking, combinatorics, is how we use, or it's about clever ideas for counting large things very cleverly and without manual labor. And this has a lot of applications, again, whether it's in cryptography or compression, probability theory. So if you're a data scientist, counting, or you need to know combinatorics, and there's no two ways about it. Complex numbers, of course, which has to do with imaginary numbers and real numbers. We're not going to get at that today. And analysis, which is calculus at a higher level. So it's concerned with things like infinity, series, limits, sequences. Once again, this is something you may also want to maybe put on your bucket list if you're a data scientist, because in probability theory, there is an extension of this. There's another branch of mathematics that is of concern to probability theory, and probability theory is called measure theory. And measure theory, for it, the prerequisite is analysis. So really what I'm trying to make out the point I'm trying to get across is here is that discrete mathematics it really is your gateway to the most amazing and intelligent ideas in mathematics. This is a topic you really want to invest time and effort in. It will pay off greatly in your career as a software engineer or a data scientist, or you may be an engineer. I mean, in any aspect of our world where mathematics is applicable, and should you want to be proficient in that particular uh, field of work, discrete mathematics will really take you far. But let me draw your attention now here to the slide. I told you that discrete mathematics is a subset of pure mathematics. And if I were to classify discrete mathematics, and my classification is based on what I've seen in books on discrete mathematics, well, it will be most of what you would find in pure mathematics, excluding complex numbers and analysis. Why? Because these two particular topics are concerned with, well, non-discrete things. And to say something is discrete is to say that it is whole. It is not continuous. A number that a number that is whole is something like uh, an integer. It is not. There is no decimal involved. There are no fractions involved. All right. Now let's talk about algorithms, logic, and propositional calculus. Now logic is about deductive reasoning. It is about going from a set of premises, a set of statements, and then arriving at one conclusive statement. And to perform such an operation, where we go from a set of premises or a set of arguments to some conclusive statement, you'll perform some sort of calculus on these premises. That is what propositional calculus is. It is about dividing your arguments into statements and then performing calculations on them like you would in algebra. Although the rules here are different and the operations that you perform on these premises are different. But again, it's not something difficult to do. It is something that is very natural to us as human beings. Logic, that is. And if you've tried programming before and you've come across if and else statements, and you probably know how that they're quite easy. Assuming you're already familiar with the syntax, then you know they're pretty easy to implement. Of course, there will be situations where you're not doing a small number of logical operations. It can get quite elaborate, but it is important for proofs. If you want to be able to, like I said, read and even write your own proofs, then propositional calculus is a necessity. But when it comes to applications in computer science or even data science, logic is at the heart of machine learning. It is at the heart of game theory. And one of the applications of game theory is, for example, how to set up rules to prevent fraud or to increase customer acquisition, or to prevent customer attrition or employee attrition. it is used in natural language processing. So I'm sure you've all, uh, if you've used Gmail and you're trying to write a sentence and you find that Gmail completes the sentence for you, or when you are texting and the operating system is able to correct your text. Sometimes they make mistakes, of course, but usually they get it right. Well, in all of these examples, propositional calculus is at the center. The programming implementation of ideas in propositional calculus are implemented. So, so we will shortly switch to the tutorial and talk about this. But here's where propositional calculus is directly applicable with respect to algorithms. When it comes to computer algorithms, and what again, let's pause right here and define an algorithm. What is an algorithm? It is a sequence of instructions for the computer. And these instructions can have different variations. If you look at the slide here, they can either be sequential, where you are instructing the computer to do one thing after the next in that order, or they can be selective. You can program a computer or you can instruct the computer to do statements, but in a conditional way. So, for example, uh, let's say the user types in a username and password. If the username and password is correct, then perform these set of operations or these set of instructions. Otherwise, perform those other set of instructions. So it can be, all right, let's log them in and welcome them and pull up their profile picture and their uh, website preferences. Or we can redirect them to the registration page and tell them what the registration process requires. And, well, that could be another set of instructions. A third uh, type of algorithm could be an iterative algorithm where you repeat a statement again and again until some condition is satisfied. So, for example, if you have a subscription on your app, if you have a newsletter, for example, you can send all those all of your subscribers emails until until you've reached the last user, and then you will not stop this emailing process until you have reached the final customer. Now, of course, complex algorithms will be a combination of all of these three, and one of the problems you will encounter when you're working on complex algorithms that have selectivity and iteration involved in the mix, you will end up with something, and you may have heard of this before, spaghetti code, where it is so problematic and so prone to breaking that you, as the program, wouldn't even want to touch it. But on one hand, you're afraid of touching it so that it doesn't break. On the other hand, you don't feel confident that it will work all the time. And what you want to be able to do, or what you'd like to be able to do, is to reduce the complexity, to maintain the capability of the algorithm, but also reduce complexity so that it is uh, you know testable and efficient. You may have heard of something called time and space complexity, right? You can have two algorithms that do the two that can do the same thing, but one is far more efficient than the other. In fact, uh, the efficiency of that, the difference in efficiency can really uh, be more pronounced when the data is larger or when more users are involved. So how do you go about reducing a very elaborate algorithm and make it more concise and efficient? Well, if you are able to recognize what parts of the algorithm could be collapsed or to which parts of the algorithm you can apply propositional calculus, then you will be able to do that. You will be able to write very effective and elaborate algorithms if you have this mathematical foundation. And it really doesn't take much to learn propositional calculus, and we'll very soon look at a tutorial. Right. Now, data structures and graph theory. A data structure is uh, analogous to a mathematical structure, right? We said it's a thing that contains elements. In programming, we have similar ideas, but we call them data structures. They are mathematical structures that contain data as elements. In programming, we could have an array, or there is something called a graph, or it could be a binary tree. Now, if you are a programmer, or if you're someone who is just learning programming, then the first thing that you will encounter is a linear data structure, something like an array. And Python, they're called lists, uh, sets as well, sets, tuples. These are linear data structures, and these are obviously they have very wide applications, but they are not the right data structure in every scenario. Uh, a more useful type of data structure, or a more useful category of data structure, is the nonlinear data structure, or we can call them graphs. These are widely used in social media applications and databases, uh, in the Internet of Things. They're quite powerful, but they can get they can be quite complicated, and some of these will require mathematical literacy. At the very least, you should be able to understand what some concepts are in graph theory. You need to know what is for example, a graph, a multigraph, a path, the different types of the different names we give to graphs, because they have names, and these names will be referenced in order to explain an idea. And if you want to know what the explanation is, well, you will come across some mathematical expression. So once again, to become a very advanced or elite software uh, programmer or data engineer, or if you're in the world of finance, you want to write algorithms for financial or algorithmic trading, then uh, you will invariably come across graph based data structures. And if you want to understand them and implement them on your own, you'll have to have the mathematical foundation. But let me at least give you a high level illustration before we turn to the tutorial and we can talk about the mathematical syntax. Right? So I said we have two types of data structures. We have arrays, in which elements are put in some linear order, and arrays are they're pervasive, right? Many things come in tabular form, in the form of rows and columns. That's how we store data a lot, but not always. And this particular type of data structure is not appropriate in every situation. The second type is the graph data structure, a subset of which is the tree data structure. Now, this is a graph. And very quickly, let me introduce you to some terms. These circles we call the vertices, or they go by another synonym, nodes. So these are either nodes, you can call them nodes if you want, or you can call them vertices. Now you can see that we have these lines that go from one vertex to another. These lines we call edges. So very simply put, a graph is composed of two things: a set of vertices and a set of edges, and the edges are the connections between the vertices. Now, of course, if you see here, we also have this edge that comes back to the same vertex. Understanding graphs will also allow you to understand something called finite state machines. Finite state machines are at the center of many things, from vending machines to physics to regular expressions. And if you're not familiar with regular expressions, it is a form of programming, and it is central to applications like natural language processing and natural language understanding. Moreover, and also another application of graphs, or being able to understand graphs, is building complex stateful machines. Uh, complex applications with very complex user interfaces require states. This something called a state that is well formalized, and it has to be something that is well planned ahead of time. If you want to be able to build such applications with very elaborate user journeys, well then you need to be able to formulate these mathematically. And once again, the mathematical subject that discusses such ideas is discrete mathematics. Now, a graph is a data structure that has edges to multiple vertices. A special type of graph is a tree. It's a special type of graph in which the edges are not circular. They do not go back to the same vertex again. So it's very one way. You can see here in this particular graph, and to introduce some terminology, we call this a typically in trees we call these vertices nodes. But again, the word is interchangeable. So we have these nodes, and then we have these sub branches. We have the branch on the left and the branch on the right, and we call the edges at the end of the tree. This is like a tree turned upside down, right? Where the roots of the tree are at the top and the leaves are at the bottom. So if you can imagine a tree that is turned upright. So if we have a node that does not branch off to any other node, we call those leaves, right? Because, well, it's analogous to a tree, right? It turns out trees are very good for searching for values very quickly. Let me show you an example of a binary tree. Now here's a binary tree, a better pictorial representation of it. And if you haven't seen one, take a moment to see why it's ordered the way it is. So this is a sequence of numbers from 1 to 21. Some of the numbers are missing. But the binary tree is arranged, and really its purpose is to search for values very quickly, efficiently, when the position of that particular value is unknown. So if you see here, the smallest number in this set of numbers is 1, which is at the very far left. And if you look at the very far right, you will see that it is the largest value of this collection. And then if you look at the root node, or the root vertex if you like, we have the number 10, which is the number between 1 and 21. If we have an array, which is a linear collection of numbers, then searching that list for a particular number can take, we say, linear time. If you remember earlier, I mentioned something called time complexity. It's time complexity, worst case, and in the worst case, we denote worst case with O of n, uh, with big O. It will be n. What does that mean? It means that if you have a list with 100 values, and let's say you're searching for the number 100, let's say you have a list of numbers going from 1 to 100, and you do not know, for some reason, you do not know where the number 100 is. If you want to find that number, you have to start counting from left all the way to the right. And it's called, and it's O of n because the number of times that you have to search for the value is equivalent to the number of elements you have in that list. So if you have 100 values and you're looking for a particular value, worst case scenario will be at the end of the list. So you have to go through the entire list to find what you're looking for. Now, of course, you could be lucky and it appears somewhere in the beginning or maybe in the middle. But when we calculate the time complexity of an algorithm, we want to count, or we want to take into account the worst case scenario. We want to be prepared for the worst possible scenario. Now, with an array, the problem can get exasperated and the time complexity can be greater as the data structure gets bigger. So if you have 1,000,000 values or 10 million values, worst case scenario, you have to search through the entire collection of 10 million values to find what you're looking for. So it's not efficient. Arrays are not efficient for searching for things when the position of that thing is not known. Enter the binary tree. So you see here we have, like I said, a range of values from 1 to 21, and at the root we have the number 10. So say you're looking for the number 17. The way you would search for the number 17 in an array is to start counting from left to right. Whereas in an array, you don't do that. In a binary tree, I meant to say, you don't do that. In a binary tree, you go to the root node and you ask yourself this, or this is what the algorithm will do. Is the number 17 less than or greater than 10? Well, it's greater than 10. And because it's greater than 10, we can eliminate the entire left branch altogether. So we don't even have to look at this part. Now then we turn to the right branch with the node 19. And we ask, is 17 less than or greater than 19? It's less than. And so now this is a very shallow tree, so it will take, we have reached our matching element. But I hope I get the idea. We were able to have the search time using this data structure. Now, the time complexity of the binary tree, the binary tree data structure, in terms of big O, in terms of the worst case scenario, is log base 2 of n. Why log base 2 of n? Because you are repeatedly having each branch. So it's even better than having the search time. So if you want to search for values whose positions are not known, this is the data structure you want to go with. Now, like I said, this is one variant of a graph data structure. So trees are variations of graphs. Databases implement something called a B tree. Databases have to be able to contain large volumes of data, but also make it. They also have to be very quick in finding a particular value in the large collection. So they implement something called a B tree. If you want to learn more about those, like I said, look at the video description to learn more about graph data structures and graphs in general. Very quickly now, let's talk about the applications of what we've talked about with respect to discrete mathematics. and then we will switch to VS Code to start our tutorial. Now, again, what you see on the left are the topics that will be covered in discrete mathematics, and on the right we have the applications of these topics. Sets are uh, the first thing that you will deal with in programming, in data science, or for that matter, anything in mathematics. But of course, being able to read the notation, set notation, is a prerequisite for being able to read uh, any text on data structures. So, for example, we have two well-known books on data structures and algorithms. One of them is from Corman et al. On introduction. It's called Introduction to Algorithms, and the other one is from Robert Sedgwick. And the title of the book is also Algorithms. So you will find a lot of set notation in those books. If you want to be a master of data structures, then you need to be able to read those books. And if you want to be able to read those books, you have to be very, very familiar with set notation. But of course, this is not just limited to those books. Like I said, sets are ubiquitous in all of mathematics. Probability theory, abstract algebra, calculus, linear algebra, and calculus. So, if this is your first time hearing about discrete mathematics, that should be your starting point. Logic, we talked about logic and how it is important to writing efficient algorithms. Algebras, and once again, I'm referring to an algebraic structure. This one, again, is something ubiquitous in higher level mathematics. Well, for example, if you want to understand computer graphics, which uses a lot of, computer graphics and computer vision, they use these fields use a lot of advanced mathematics, and a big part of it is, of course, understanding things like vector spaces. And linear algebra is central to computer graphics and computer vision. And if you want to read linear algebra and really understand concepts in linear algebra, the prerequisite is abstract algebra. And how do you learn abstract algebra? Well, you need to start learning sets. Because once you learn sets, then you can understand the derivations of sets. So things like fields, rings, groups, vector spaces, etc. Cryptography. I mentioned this before. At the heart of cryptography are prime numbers and divisibility, which is what congruence is about. Compression. So how does compression work? Compression tries to use bits to represent encoded characters. So if you've heard of UTF-8 or UTF-32, and let me show you something very quickly. So this is how encoding works. To encode means to represent alphanumeric characters or all types of characters that can be represented on the computer using a specified number of bits. So for example, in UTF-8, in a UTF-8 encoding scheme, you use 8 bits of characters to represent any type of character. Whereas in, for example, UTF-16, you use 16 bits of characters. Why does this matter? Well, the more bits you allocate to a character, the more character variation you can store. Yes, because the more bits you have available, the more characters you can store. Now, it's nice to be able to represent all kinds of characters. The problem is every single character will then take that much of space. So for example, if you have a file with UTF-32 encoding, each character that you put in a file, let's say you have a text file, right? And you set set the encoding to UTF-32. Every single character that you type into that file will consume 32 bits of space. Even a space, even a period, even a comma will take up 32 bits of space. This will take a lot of disk space very quickly. So when possible, you want to choose the appropriate encoding. If you're going to be using only English or Latin letters, you can use something like UTF-8. But if your file is going to contain other languages or, let's say, mathematical symbols, you will need a different encoding scheme. So how does compression work? One type of compression technique is to vary the number of bits. So as opposed to allocating every single character the same bit allocation, a compression algorithm will change the number of bits. If there's, for example, a character that appears frequently like a space, well, we can represent the spaces with a smaller number of bits. And there's a way we can arrange the bits so that when we decompress the file, we get the original file. What is the mathematics that concerns, or what is the mathematics that you would need to understand to read and implement compression? Well, the prerequisite is relations, which we'll look at in a moment. Functions have very wide uses. Functions are very fundamental. But if I can give you one of many instances, it would be abstraction. Functions, in programming at least, allow you to abstract away sequences of code or sets of instructions, which we call an algorithm, for later use. And then you can take multiple functions, abstract them again into a super function, if you like. But that's not the best word. What I'm referring to is a class. Classes allow you to do object-oriented programming. So the larger your application gets, the larger your program becomes. You want to introduce more and more abstractions, and functions allow you to do that very effectively. And then, of course, counting, which I said is another name for combinatorics. And by the way, discrete mathematics, once again, according to the Princeton Companion to Mathematics, discrete mathematics is sometimes known as combinatorics because this mathematical branch, this discrete mathematics, is about using different techniques to represent numbers, to reduce complexities, to know the different number of ways in which mathematical objects can be arranged. And of course, one example I put here is approximation. How to approximate a very large number or a continuous number using bits, which is what computers do after all. So these are only a small number of things that you would be able to understand if you are able to read and understand the items on the left. So if you want to be able to work in these areas, then what you see on the left is a prerequisite. All right. Now let's go ahead and switch to VS Code and let's do a brief tutorial in discrete mathematics. So these are the topics that we are going to cover. First of all, this is VS Code. It is a IDE, which stands for Integrated Development Environment. You can download this from Microsoft. But basically, what I have here in the left panel is a Markdown file, which allows me to, create. So first of all, on the left I have a Markdown file. On the right panel, I have a preview of the Markdown file. So this is a render of what I have on the left. So basically, I can use 3 ampersand signs to create a level 3 heading. I can use dashes to create a bullet point. And then I can use the LaTeX. This is called LaTeX. You see these dollar signs? They allow me to write or type out mathematical symbols. So it's much neater than writing it on like a blackboard. But yeah, basically what we have on the left is a markdown file. You'll, if you look at the video description, you'll see where to find this. And on the right, we have the preview. Let's actually just switch to the preview itself. Again, this will be a very short tutorial. If you want to go into all of these in more depth, check out the video description. So we'll cover sets, functions, some propositional calculus relations, and then I will switch to show you graphs visually. That would be a more efficient way to understand graphs. Okay. Now there are many other symbols in discrete mathematics. I'm only going to show you like a handful of these. Okay, so these are the symbols, the names of these symbols, and I'll show you how they are going to be used. So a set is what? A set is a mathematical structure. That is, it is a collection of objects to which some rules apply. Now, if you look here, we have a set A, and you can see that it's pretty straightforward to define a set in mathematics. And once again, you have your curly brackets, you have your objects. In this case, we have numbers, and then you assign to it a variable. Here we have A. Now, sets, of course, can also contain other objects, so they don't have to be numbers. So, for example, here we have 5, 6, which are integers, and then we have the set A, or a set containing the set A, the function f, which is defined down here, and we have some vector b, whatever that is. So just like in Python or other program languages, where you can declare an array and put mixed data types in that array, you can do the same thing in mathematics. Okay, this is not doing anything particularly useful. It's just to show you the programming equivalent of this mathematical expression up here, or the mathematical expressions up here. So doing this in Python would look something like this. You would declare a dictionary. You would declare a set. Okay. And if you want to define the function f, you would have define keyword followed by the name f, the parameter, and the return value of the function. If you look here in the programming block, the function f returns the length of some set, where some set is a parameter. So if you want to call this function, you would say f, so something like this, right? Something like this. If you want to call the function, you would do it like so. So with f, and pass a, the set a as an argument, and this will return the length. So how many items do we have in the set a? Well, we have 5. You will get 5. That will be the return value. Once again, in Python, the ampersand is a comment. So if we call this function, you will get 5 as the return value. Well, if you look up here, this is the mathematical equivalent. We have these 2 vertical bars. We call this the cardinality of the set. It's a big word, but all it really means is the number of elements in that set. So this is, by the way, map notation. We'll talk about function in a second, but this is map notation. Basically, we have map, which maps, we have a map f, which maps the set A, or the elements in the set A, to the cardinality of that set. Okay, so it's a map that, functions are maps, by the way. Functions are types of maps. A function will take the set A and map it to its cardinality. So you will get the set and the number of items in that set. And then we have functions. I just alluded to this, but we have 2 ways to defining functions. You can either define them as maps or as equations. So let me show you both. Up here we have a function sum, a Python function sum, which takes as argument number a and num b. So these are the parameters of the function. And then in here we have, in the scope of the function, we have another variable num c, which is the sum of, well, these two numbers, which is then returned by the function. So if you want to define this function in mathematics, we would say let sum, which is the name of the function, and a colon. And what the map sum will do is it will take you from two real numbers to one real number, right? Because that's what we said the sum function does. So let sum map from the real number system to the real number system be a function defined as, well, as you see, it is expressed here. It is a function that takes two variables, and then it will be equivalent to the sum of those two variables, which we can also refer to as num c. Now, if you want to call the function, and print its value, we can call the sum function and pass this sum function as the argument of the print function. And this is what we call in mathematics a composition of functions. So how will Python process this? Well, it will first evaluate sum. So you will get the number 5, and then pass that to the print function. And let's not forget the rules with parentheses. Whenever you have multiple parentheses involved, you always go from the inside and work your way out. So since we have 2 and 3, this is the innermost pair of parentheses. We will evaluate that first and then go out. The equivalent of this in mathematics would be to compose a function as follows. So we have one function called print and sum, and we indicate that with this circle, this big circle, and then the arguments right after that. So a composition of function, this expression is equivalent to that. Once again, this is math, not programming. Okay? So these two are equivalent. And here's an example of defining a function with control statement. So here we have a function check exists, which takes the parameters element and the set. So basically we'll see if this element exists in set and return true and false otherwise. And if we want to create a function with a control statement in mathematics, we do it this way. This is called a piecewise symbol. This is a piecewise function. So it will return true if the element is in A. Do you see this a character that looks like an E flipped around? Well, this is pronounced in. So element in A. So if the element is in A, then we will return true. Otherwise, if the element is not in A, we will return false. All right. Let's move on to sets now. Let's look at the union and intersection operations. Say we have two sets, A and B. So the set A is the numbers 1 through 5, and B is 6 through 10. What if we want to combine these two sets, or if you want to take the union of these two sets? Where in Python we have the method called union, right? A union B, and what we will get if we run this code is the set containing all 10 values. And let me just modify this because this is not an assignment. Rather, I meant to say that this is a comment. Okay. So I did not mean to put that equal sign. I just meant to say that if you call this function, you will get that set. All right. How do you perform a union in mathematics? Well, you have the same two sets, A and B. I just had to correct that. I meant to put B here. So we have two sets A and B. To take the union of the two sets, we have this symbol, this U-looking symbol. We have this U-looking symbol, and I just made sure to put the curly brackets. So that's what the union does. Okay. And then the intersection. What is the intersection? Well, the intersection of two sets is when you create a third set that contains the elements common to both sets. If you see here in Python, if you were to run this, you would have an empty set. Why? Because, well, there is no number that is common to both of these sets, which is why this is empty. And in mathematics, if you want to take the intersection of two sets, you have the same looking symbol, but it's turned upside down. Okay, so that's the intersection of A and B. And since they have no elements in common, we get same a set with no elements in it. And by the way, in math, when we have a empty set, that is also called a null set, which can be also represented with this zero-looking character with a line that goes through it. Let's look at propositional calculus. So this is a very simple if and else statement. We have two variables, p and q, both assigned to true, and v equals to false. Well, what happens if we print p and q in Python? Well, we get true, right? Because the AND operator will check to see if both statements are true. And if we do p and v, since both conditions have to be true and one of these conditions is actually false, v that is, we'll get false. And but we know that we can also have complex truth statements. So here, what we're doing is we have q and v as one statement and p as another statement. So what we want to do is evaluate these two statements. Well, again, with the rules of parentheses, we have to evaluate the innermost parentheses and then go up. So how do we evaluate this? First, we evaluate q and v. Well, q is true, v is false. Only both of them have to be true, one of them isn't, so this will be false. And since this is false and this is true, and they're both supposed to be true, well, once again, we get false. Okay? And then we have the not operator. So if this statement is true, then the exclamation will give you the opposite, the complement. That's the word we want to use, the complement of this expression. So since this is true, we apply the complement and we get the opposite, which is false. And this is the equivalent of the above in mathematics. Okay? So this is the AND operator, the OR operator, and then of course when you have multiple statements, you want to make sure you put in the parentheses. And up down here we have the complement. So we have this kind of L-looking character. That's the complement. So this is the equivalent of that up here. All right. Now relations. This is a very small example of this. Is just to make clear what a relation is. Just check the video description to find a more complete tutorial. But let me give you one quick example of where relations are applicable. In MapReduce, if you're a data scientist or data engineer, understanding relations, set relations, can really help you with applications like MapReduce. So what is a relation? A relation is a set that associates two other sets. Or you can, if you want, you can go with the definition that I've put here, that a relation explains the association of two or more sets. So let's say we have the relation R, which is a set with tuples. If you look at the set, you'll quickly understand what's going on in here, right? We have a city and the country in which it is located. City and the country, right? So that's the relationship. So this relation is the association of two other sets, the set A and set B, where set A is the set of cities and B is the set of countries. So if we want to say that Chicago and the United States go together, we say Chicago is R related to the US, which means that these two go together and they have to be ordered. So for example, when we say Chicago R US, that means we will get a tuple where you put Chicago as the first element and the US as the second element. Again, the notation is very simple, but being able to read the relations where you see them and being able to recognize them where you see them is going to make a huge difference in your journey to learning, by the way, graphs. So the prerequisite for understanding graph theory, which is a huge and very important branch, in fact, it has a branch of its own, graph theory, uh, is understanding relations. Now, I don't have space here to create a visual representation of a graph, so let me show you a PDF. Right? So here's a PDF that I found for you on the web, and let me make sure you can see the text. So this is what I mean when I say you want to be able to read mathematics uh, to make sense of concepts in either computer science or data science. So a graph is defined as a space, and a space is a set of points, or a space is a set of sets. So G is the graph, and it contains V, which is a set of vertices, and E, which is a set of edges. Okay, so if you look here, down here, this is the graph. Your vertices are V1, V2, V4, V3, and V5. All right. And of course, we have a set of edges, which they have not labeled in here. But the edges, of course, are these lines that go to the next, go from one vertex to the other. One way to represent graphs are with matrices. This is what we call an adjacency matrix. It basically tells you which vector goes to which vector through what edges and how many times. So this is, let's say, the column for the first vertex. It tells you that it has one edge going to itself. You see here, let me zoom in. It has one edge going to itself. Then it has three edges going to the second vertex. That's one edge, second edge, third edge. So three edges going to vertex 2. It has 0 edges going to vertex 3, and if we look carefully, we can see that that vertex 1 has no direct edges to V3. So that's why we get 0. And then if we come to vertex 4, it says that we have 3 edges. Do we have 3 edges? Yes, we do. We have 1, 2, 3. Okay? We don't count that one because that's just from V4 to V4. And then again, we have no direct edges to V5, so we get 0 in here. And if you continue this way for the other vertices, you will have completed the adjacency matrix. Now, what's nice about this is that you can use linear algebra techniques or matrix techniques to evaluate the structure and the paths of a graph. And this has, well, I will leave it to your imaginations to see, I will leave it to your imagination to consider the applications that this can have. But this is very, it has many applications. Now, there is not a lot of, there's just not enough time for me to cover all of these. So if you want to learn a lot more about the topics that we have discussed here today, especially graphs and their applications, check out the video description. This is a short tutorial. There's a more elaborate tutorial. Furthermore, there's an entire course on everything we talked about. So let me just switch now to the slides again to talk about the course. If you want to learn more about the course, mathematics and programming, visit this website. The link is also in the video description. And let me show you the page. So you want to scroll down to the upcoming courses and mathematics and programming. Click on Learn More. And what you want to do is check out the lesson plan. So if you can scroll down here, read all this information, and then click on the lesson plan to see the structure of this course. Remember that we have a Slack channel where everyone will be participating and where you can ask your questions. So if you do have any questions, just scroll down, click on the link to the Slack channel. You can also find it on the main page. All right, click on the Join Slack to ask any questions you have about this course. Okay, but that's it for this session. I want to thank you for watching. I look forward to seeing you in the next one. Until next time, take care and bye-bye.